The year is 1350 BCE. You are in Egypt. The temperature is sitting at around 43 degrees Celsius. That is 110 degrees Fahrenheit. There is no air conditioning. There is no ice. There is no cold drink anywhere on the planet, because refrigeration will not exist for another 3,000 years. You are standing on sand hot enough to fry an egg. You are wearing a linen kilt. You are about to spend the next several hours doing heavy physical work outdoors. And you are not suffering. You are not enduring. You are not counting down the hours until it is over. And here is the thing that took me a long time to sit with properly. The people living in ancient Egypt were not tougher than us. They were not built differently. They had the same body, the same sweat glands, the same 2% margin before the brain starts going soft. What they had instead was something far more interesting. They had figured it out, not through genius, not through one great invention, through thousands of years of quiet observation, of passing down what worked and quietly dropping what didn't, until the accumulated result looked almost designed. Ancient Egypt solved the problem of surviving extreme heat so thoroughly and so elegantly that in several important ways we have not improved on it. We have just added electricity. The body first. Before any of the engineering makes sense, you need to understand the problem it was solving. Your body has exactly one serious cooling strategy: water. When your core temperature rises, your body pushes water through the skin, and when that water evaporates, it carries heat away with it. That is the entire system. In the Egyptian summer, a person doing outdoor labor can lose several liters of fluid in a single day. Lose 2% of your body weight in water and your thinking starts to slow measurably. Lose 5% and you are in genuine danger. Lose 10% and you are dying. And you may not notice, because one of the first things that heat takes from you is the ability to recognize that something is wrong. But water is only half the problem. Sweat is not pure water. It is salty. And when you sweat heavily for long enough, you can drink as much water as you like and still collapse, because you have flushed out the sodium your nervous system depends on to function. The condition is called hyponatremia. It will kill you with a full water jar in your hand. So the problem ancient Egyptians were quietly solving every single day came down to three things. Reduce how much heat enters the body, replace the water being lost, replace the salt being lost. Everything that follows is just increasingly clever ways of doing those three things. The building as the machine. Start with the house, because this is where the Egyptians were quietly extraordinary. Egyptian homes were built from mud brick, Nile silt mixed with chopped straw, pressed into molds and baked hard in the very sun the wall was designed to defeat. It is a satisfying irony, and mud brick has a property that modern construction has spent considerable effort trying to replicate. It has enormous thermal mass. What that means in practice is this: a thick mud wall does not block heat, it delays it. The afternoon sun strikes the wall and the heat moves through it slowly, taking many hours to reach the interior. By the time the peak heat of the day arrives inside the house, it is closer to midnight, when the desert has cooled and you actually want some warmth. The cold of the night then crawls back through in the other direction and arrives inside around midday, precisely when you are most desperate for it. The wall is not insulation. It is a temperature delay system. It takes the daily swing between desert noon and desert night, which can be 20 degrees Celsius or more, and shifts it so that the house is always slightly out of phase with the worst of what is happening outside. Nobody was calculating thermal lag coefficients in 1350 BCE. They just noticed that thick walls made the house more bearable, and they built accordingly for 3,000 years. On top of that foundation, they stacked further refinements. Windows were small and positioned high on the wall near the ceiling, because hot air rises, and you want its exit point as high as possible. Streets and worker settlements were kept narrow. so that the buildings shaded each other through the hottest parts of the day. Rooms were arranged so that the spaces used in the afternoon sat on the shaded side of the house. And the roof.
Egyptian rooftops were flat and were treated as functional living space. In the hot months, a substantial portion of the population simply moved their sleeping arrangements to the roof, where air could move freely and body heat could radiate away into the open sky above. Sleeping on the roof in an Egyptian summer was not a sign of hardship. It was the most comfortable option available. The wind catcher. Now here is the part that should make any engineer stop and think. Egyptian houses featured a structure called a malkaf. It appears in tomb paintings, most clearly in the tomb of Nebamun at Thebes, dating to around 1300 BCE. It is a hooded vent mounted on the roof, angled to face the prevailing north wind. Wind enters the scoop, travels down a shaft, and is delivered directly into the rooms below. Meanwhile, hot air in the interior rises and escapes through those high windows on the opposite side of the house. You have created a pressure difference. Cool air in from the north, hot air out from the top. Continuous airflow through the living space. No moving parts, no power source, no maintenance beyond repairing the occasional storm damage. And then some households took it one step further. They placed porous clay water jars in the path of that incoming air. Water slowly seeps through the clay surface, evaporates on contact with the moving air, and evaporation removes heat. The air reaching the room below has been cooled by passing over a wet surface. That is an evaporative cooler. It operates on the same physical principle as units you can purchase today and plug into the wall. The ancient Egyptian version required a clay pot and a gap in the roof. This technology did not vanish. Wind catchers spread and evolved across the Middle East and into Persia, where tall wind towers called badgirs still stand in the city of Yazd in Iran and still function as they were designed to. The engineering did not become obsolete. We simply found a way to do something similar using electricity and largely stopped thinking about it. Clothing. The intuitive response to extreme heat is to wear as little as possible. The Egyptian answer was more considered than that, and the reasoning is worth following. Egyptian clothing was almost entirely linen, produced from flax, and the choice reflects a particular set of material properties that align very closely with the demands of a hot, dry climate. Linen is highly breathable. The hollow fibers allow air to pass through the weave. It is effective at wicking moisture away from the skin and spreading it across a wider surface where it evaporates more efficiently. And it is a poor insulator, meaning it does not trap the heat your body is already trying to shed. Cotton, by comparison, holds moisture against the skin. Wool insulates. In that specific environment, linen is close to the ideal fabric, and Egyptian civilization recognized this early enough that flax cultivation became one of its foundational agricultural industries. There's also something counterintuitive worth noting. Loose, light-colored fabric worn over the skin can actually keep you cooler than bare skin in direct sun, because it blocks solar radiation while still allowing sweat to evaporate. The fabric provides shade. You sacrifice a small amount of airflow and gain a significant reduction in heat absorbed from above. It is the same logic that drove desert peoples across North Africa and the Arabian Peninsula to converge independently on flowing robes rather than minimal clothing. The physics pointed in the same direction every time. Wealthier Egyptians, and particularly priests, shaved their heads and wore wigs. This had practical advantages beyond fashion. A wig sits slightly above the scalp, creating a small ventilated air gap. It can be removed. Your own hair cannot. The scalp beneath can be kept clean and cool on demand. Hydration. The Nile was the source of life for Egyptian civilization, and it was also not something you would want to drink directly. The river carried silt, parasites, animal waste, human waste. Drinking untreated river water carried real risk. The solution was beer. Not occasional beer, structural beer. Beer consumed in quantities that today would seem extraordinary. because the alternative was drinking from a river that could make you seriously ill. Egyptian beer was not what we would recognize by that name. It was thick, low in alcohol, made from barley or emmer wheat, and nutritionally substantial enough that it functioned more as liquid food than as a drink. The brewing process involved heating the grain, and fermentation produced an environment hostile to many of the pathogens that made raw water dangerous. Beer was, for practical purposes, a safer source of hydration than the water it was brewed with. Salt in diet. Replacing water is only part of the equation. The Egyptian diet addressed the salt problem almost incidentally, through foods that happened to provide what heavy outdoor labor in extreme heat depletes. Bread was the staple, dense and made with salted grain. Preserved and salted fish was common. Dates and figs provided potassium. Onion and garlic appeared frequently. None of this was constructed as a deliberate electrolyte strategy. There was no understanding of sodium ions or mineral balance in any formal sense. But a diet built around salted, preserved food, consumed alongside large volumes of low-alcohol beer, produces something close to what modern sports nutrition would recommend for people doing sustained physical work in heat. That is the pattern that appears throughout this story. Not theoretical knowledge, but accumulated practical wisdom. Thousands of years of doing what worked, noticing what did not, and passing the difference on. The working day. The simplest part of the solution is also the most overlooked. The Egyptian working day was structured around the sun, not against it. Work began before dawn, when the air was cool. Heavy labor was concentrated in the early morning hours. The middle of the day, the genuinely dangerous window, was treated as time for rest, shade, food, and sleep. Work resumed as the sun began to descend, and the temperature followed. The records from Deir el-Medina confirm this. The workers operated in organized shifts and had designated rest periods. Many of them stayed in temporary structures near the work sites during the working season rather than crossing open ground in the midday heat each day. Even the great construction projects appear to have been organized in part around the agricultural calendar. The annual flooding of the Nile made farmland inaccessible and made a large workforce temporarily available, while also providing ideal conditions for moving heavy stone by boat. The work year, like the workday, bent around the natural rhythms of the environment rather than trying to override them. What this actually means. There is a house in Egypt 3,500 years ago, thick mud walls holding the cool of the previous night, a windscoop on the roof drawing the north breeze down into the rooms below, a clay jar sitting in that airflow, its surface slowly sweating, cooling the air that passes over it, a family sleeping on the roof under a sky with no clouds in it, a jar of beer for the morning. Not one part of that house requires electricity. Not one component can fail in a way that cannot be repaired with earth and water and a few hours of work. It has no off switch because it has no on switch. It simply works, continuously, as long as the wind blows from the north and the Nile keeps flowing. We solve the same problem by placing a machine in the window. That machine takes the heat from inside the room and deposits it into the street outside, raising the ambient temperature, which means neighboring buildings need larger machines, which deposit more heat into the street. It is a solution that generates part of the problem it is solving. Architects and engineers today are going back to study the tomb paintings at Thebes, the windscoop, the thermal mass wall, the evaporative cooler made from a clay pot. These are being reconsidered seriously as building temperatures rise and the cost of running mechanical cooling systems increases. The Egyptians arrived at their answers not through engineering theory, but through thousands of years of careful attention to what made the afternoon bearable and the discipline to pass that knowledge forward. The answer was never toughness. It was mud, linen, shade, salt, and paying attention, and it worked for 3,000 years.